Hello and welcome to this session. It is called Avoiding Pipeline Leaks, or how I learned not to trust my CI/CD system. I only have 4 major points that I want to go over today, specifically the who, the what, the why, and the how, and I'm going to start off by quickly introducing myself before I'm going to move on to some more important things like what, why, and how. The what will involve a quick rundown of a fictional company called HashiCorp, its employees Melbourne and Dave, and their infrastructure, as well as some technical aspects of said infrastructure. Then we'll go over JSON Web Tokens and how they're important in the context of Vault, as well as talk a little bit about HashiCorp Sentinel, and we'll finish that off by talking about the integration of Vault in traditional CI/CD systems. The what is, as you might have guessed, by the numbers on display, followed by the why. This is where I will talk about the motivations of this talk, illustrated by the story of an incident at HashiCorp. After some demos, I want to come around and talk about the how, specifically how we can improve our security postures in environments like the one I'm going to present. And then we're going to wrap things up with a short summary. With that out of the way, let's get started. The who, not the band, that's me. My name is Marcus. I'm a senior DevOps engineer at FullStacks. We're a full spectrum cloud native consultancy, and my area of expertise is Vault and Terraform. If you want to connect with me, you can find the links on screen. Apart from that, there's not much more to say, so let's move on. Now let's talk about the what. What we will be working with today. As mentioned earlier, we will be introducing HashiCorp and 2 of their employees. Then we will look at the infrastructure of HashiCorp. We will go over JSON Web Token and its relevance for Vault, and then we will talk about the relevance of Vault in the context of CI/CD systems. Lastly, we will briefly go over HashiCorp Sentinel before moving on. During this talk, we're going to cover a number of events that form around the fictional company HashiCorp. HashiCorp is your typical mid-sized company that utilizes Terraform open source for most of their infrastructure requirements, Gitlab for their version control and continuous integration needs, and they've recently also deployed Vault Enterprise and have already covered a number of different use cases, but the implementation is not 100% there already. They also have 2 employees that we're going to focus on today, Melbourne, the malicious developer, and Dave, the DevOps engineer. As we can see here, HashiCorp uses the cloud offering from Gitlab, gitlab.com, with Gitlab CI runners deployed on an on-premises Kubernetes cluster. Said runners are configured in such a way that they can authenticate to HashiCorp Vault using JSON Web Tokens. These runners are mainly used to deploy Kubernetes applications on the dedicated deployment cluster that we can see here using Terraform open source, the state of which is stored in GitLab. The pipelines are configured as such that they retrieve the Kubernetes service account tokens used to authenticate to the deployment cluster from Vault, and secrets are automatically exported as the respective environment variables for the Terraform provider configuration. Now let's take a look at JSON Web Tokens and delve a bit deeper into the topic. As you might know, JSON Web Tokens are basically just 3 base64 encoded strings in a trench code, or rather separated by 2 dots. They consist of a header that contains information about the token type as well as the hashing algorithm used by the signature, a payload that consists of some JSON data, fun fact, that's why it's called JSON Web Token, and a signature that contains a signed hash of both the header and the payload from the entity that created the token. This signature allows us, assuming the private key of the entity responsible for creating the token wasn't stolen, to attestate that whatever is in the payload section came from whoever created the signature. Meaning, if the signature is from a server we trust, then we can trust the payload as well. This allows us to use JSON Web Tokens for authentication. In fact, it's the basis for OIDC, a very well-known and widespread authentication mechanism that is also supported by Vault. The nice thing here is that Vault allows us to do 2 things that will become relevant later. 1, we can pick any key from the payload to use as our user identifier. And 2, we can advise Vault to store some of the payload data in a user's metadata on successful authentication, aka login. Basically, this means we can assign any attribute, for example the project ID from the JSON payload, as the unique identifier that will be created as an alias in Vault. When we now think back to the infrastructure, I mentioned that the GitLab runners were able to authenticate to Vault using JSON Web Tokens. These tokens are issued by the GitLab server and contain a breadth of metadata about the pipeline that is issued this token. For example, the aforementioned project ID or the pipeline ID. So now we know that we can store metadata about GitLab pipelines on a per repo level in Vault. We will get to how this is useful when we go have a deeper look at Sentinel. But first, let's talk about Vault and CI systems. One of the most common use cases for Vault is to centralize secrets management to get away from variables that are set on a pipeline level and they need to all be manually changed. Because usually what you find is that secrets are spread out, some are in Ansible vaults, others are in pipeline variables, some are even checked into Git repos themselves. And people want to get away from that because the consequence of that is that access to secrets is hard to manage and even harder to audit. As I mentioned earlier, some CI/CD systems, however, allow the generation of signed JSON Web Tokens for pipeline, for example Gitlab, which enables them to be authenticated by Vault. Some even have deeper integration. Gitlab, for instance, allows you to directly inject secrets into pipeline, though last time I checked, this was only possible for static secrets. So now that we know all about JSON Web Tokens and their CI integration, I bet you're burning to know how Sentinel comes into play here. Sentinel, for those that are unaware, is a policy as code language and framework by HashiCorp. It comes included with Vault Enterprise and it can access data on Vault via its own Vault Access token. What this allows it to do is some really fun shenanigans. If you recall earlier, I said that the payload of JSON Web Tokens can be trusted if it is signed by a trusted server, and I also said that some of the metadata of a JSON Web Token can be stored in Vault whenever a token logs in. What we can do now is create a so-called Sentinel endpoint governing policy. That is a policy that can be assigned to a certain API endpoint, like the login endpoint for JSON Web Token authentication. And then we can go ahead and look at the payload of an authentication request going to that endpoint. Meaning we can now inspect JSON Web Token's payload and use Sentinel to look up the metadata stored for the user that tries to log into Vault and compare the two to make a decision based on that. These endpoint governing policies are evaluated before the user logs in, so we can deny a login based on the result of the policy. Now keep this in mind as we will pick this piece of knowledge back up later. Because first, I want to talk a bit about the why and get back to BigCorp's story as well. Now, the original question I had when I came up with this idea was that as a Vault operator, how can I improve the way that secrets are consumed, especially in shared environments where we might not always have full control over whose workloads and pipelines run alongside yours. Next question was, how can I show this off with a proper real-world example that, whilst avoidable, is still a thing? And it would not take too long for such an example to find me when I heard a story of a former coworker about them needing multi-architecture builds for their customers. They couldn't or didn't want to set up dedicated ARM hardware or use respective cloud instances. So what they chose was to emulate the hardware. That came with a little caveat of requiring build containers to run as privileged. If you've heard of security implications of privileged containers, you know that's not good. If you haven't, here's a short summary. It's bad. It's really bad. How bad, you might ask? You'll see in a minute. Now, shared environments are common, as are misconfigurations. And the demo you will see later will not solve all your problems, but it can become part of a defensive death strategy, and it might prevent bad internal actors from doing the thing. For the purposes of our story, Verizon's data breach investigation report revealed that 19% of all breaches involved internal actors. It's not a lot, but it's still a two-digit number, so the threat of internal actors like disgruntled employees is real. Now, let's turn our eyes towards BigCorp again, where we have a little incident at hand. BigCorp has, in a similar way to my former colleague's company, decided to run their multi-architecture builds using emulation, which requires containers to run as privileged. Developer Malbert, who might not be the nicest of employees, overhears that they are going to be fired in some weeks' time. Being unhappy about that, they plot their revenge. And how that revenge looks, well, we'll see in a minute, because we're going to get into a demo. In this demo video, I'm going to show off how Malbird uses a CI pipeline to break out of the build container and exploit the host system. To summarize the video you just saw again, Malbird was able to gain not only access to the host of his CI job, he was also able to gain complete root level access to the CI cluster and all container workloads running on it. He was also able to gain SSH access to the machine from the outside. Now let's imagine the consequences of what we just saw. So, as I've mentioned just before, Malbird now has complete root level access to the CI host and to all the containers on it. So what does this mean? Well, Malbird can access any container of any CI job running on the node. This means he has access to all the secrets within each pipeline container and could theoretically use this access to access a running pipeline job and steal secrets from it. For example, the Kubernetes service account tokens that are used to deploy workloads on the deployment workload cluster. Now let's take a look at how this could look like and get an idea of what the actual severity of this problem is.
Now what you're seeing here is a continuation from earlier. Remember, Malbird still has root level access to the CI worker nodes. Now I've set up a pipeline that executes a typical deployment at BigCorp. It prints out its container ID to make things easier for us, but otherwise it's a standard deployment. It uses a Gitlab job to retrieve a Kubernetes service account token from Vault, and it then uses this Kubernetes service account token to deploy our workload. Now what you can see that Malbird does here is he executes into the container using the task ID. He then steals the GitLab job, exports it on his local machine, and then uses it to retrieve another Kubernetes service account token from Vault. He then uses this Kubernetes service account token to send a simple API call to the Kubernetes API server, in this case to list the running pods in the default namespace. Now, if we continue from what we just saw and go back to our deployment, you can see in the time lapse, our deployment still continues and still does so successfully. And in the end, you will see the pod still running, the deployment was successful.
So now let's move on to the how. Now that we've established that this was avoidable, how could have we avoided this? Well, there are some obvious candidates that would and could have prevented this. First of all, running privileged workloads is always a risk, but one that can be reduced by applying defense and threat strategies, by using Terraform to minimize the amount of time secrets spent easily accessible on a container's file system, and by restricting how and how often secrets can be accessed. But this talk is about how you can use Sentinel to improve security. So let's look at Sentinel one-time login. Way back in the section about Sentinel, I mentioned it can be used to compare the metadata of a token trying to log in with the metadata from the token's last login. Well, how does Vault know which metadata belongs to which repository or pipeline? If you recall, I mentioned that you are able to freely define which key in the JSON data can be used as the user claim, as the element that identifies a distinct user. Well, one element we can use is the project ID. Each Git repository in GitLab has one, it is unique, and pipelines usually don't run concurrently. Pipelines may start a bunch of jobs that run concurrently, but they themselves are not. Well, if we assume a CI workflow where our pipeline logs into Vault using its pipeline token, we know it only has to do that once, because on a successful authentication request, it will be given a Vault token in return to retrieve secrets. Now we know any subsequent authentication request using the same pipeline token can be safely ignored. So we can use Sentinel to compare the payload from incoming authentication requests with the metadata stored in Vault, and if we find metadata for a token already exists, we can deny access. If we look at the flowchart here, the process is relatively simple. We check an incoming request if it contains a valid JWT. Then we query the Vault database to see if we find existing metadata that matches with the pipeline token that we're looking at. If we find said metadata, we can safely assume that this pipeline is already logged in once, meaning we can delay the login request. If we don't find metadata, we can safely allow the request to continue to the actual authentication mechanism. And just to be clear, this policy does not in any way interfere or bypass existing authentication mechanisms. Instead, it works on top of them. And now let's have a look at this in practice.
Now, let's look at this. We again start our prepared GitLab pipeline. We run the same steps as earlier. We exec into the container and steal the JWT. But this time, DevOps Dave applied a Sentinel policy. Since I built this pipeline to show off the policy, I've also added some delays for the workload, which, as you can see, means that we're still able to steal the JWT and use it. However, this time the workload will throw an error that we can now look for. But Marcus, I can hear you say, what's the point of this? And since the pipeline injects the Vault token into the environment variables, doesn't that mean you could just steal the Vault token? Well, yes, but we can equip the Vault token with a use limit, so we will also know if it was stolen because it will throw an error. Now, if we turn back to our pipeline, you can see the plan stage still went on successfully because we did not implement an actual error catcher there. But the apply stage will now throw an error, and you'll see in a minute what it looks like. There it is. This is due to the fact that Terraform only needs some data for the plan, but it doesn't actually validate it.
Now, let's wrap this up. First of all, I want to thank you all for joining me in this session. Secondly, I want to go ahead and mention that the demos you've seen were first and foremost meant as a fun showcase of what Sentinel can do and what you can do with it. With that out of the way, what can you do to avoid pipeline leaks? Number 1, don't run privileged containers in your CI system and limit their use in general. Ideally, using some sort of admission control mechanism on Kubernetes, like kubewarden, OPA Gatekeeper, or SUSE Neuvector. Number 2, apply defense in depth. The more layers of security you have, the better. Sentinel is one more such layer. Number 3, find other creative ways to use Sentinel. You've seen what it can do. Number 4, reduce the exposure time of secrets on disk and minimize their lifetimes through short TTLs and use limits. And lastly, number 5, use dynamic secrets where possible. That said, I hope you enjoyed the session and feel free to contact me